So before I get going with the new stuff, here is some stuff coming up. First of all, quiz 1 is going to be at the end of class on Thursday. And to get ready for that, you just want to read back through your notes. It's going to be short answer questions, what are the 3 basic unit types, something like that. And you just say like length, time, and mass. Okay, that kind of thing. Stuff that I've said in class. And then a week from Thursday is exam 1. And that's going to be a totally different format than the quiz. The quiz is just short answer questions, no calculations. You won't need a calculator. All of the exams are going to be just like the practice, the daily problems and the weekly problems. So to get ready for the exams, you want to just go through your practice problems and your, daily problems and make sure you know how to do all those and make sure you know the steps. It's not going to be those same problems over again, but it's going to be the same thought process. And then the last thing is weekly assignment 1 is posted now. I didn't look right before class, but I think I made it due a week from today. Well, if you'd really prefer not to do it before the exam, I'll take it after that. I'm not going to be strict about due dates or anything, but I do think it's all material that will be on, the exam, and so it's just more practice, so just think of it as part of your studying. Anybody have any questions about any of this? Okay. Anybody have any homework questions you'd like me to go over? So we've been doing 1D particle kinematics, and now we're going to start 2D particle kinematics. And so remember the meanings of these things. A particle is a mathematical treatment of an object where the object only exists at its center of mass. Particles do have mass. And you can never say anything about a particle's orientation from calculations. Since it just exists at a point, there's no way to differentiate between the top side and the bottom side, the left and the right. It's just a location. So there's no orientation of the body. Just a location. Kinematics. Means that we're only describing the motion. So again, let's just think of that as relationships between position velocity, acceleration, and time. And so we're not doing anything to try to figure out how things cause these motions. We're just kind of describing the motion. Soon, after we get done with 2D particle kinematics, we'll start talking about particle kinetics, where we include the causes of the motion, forces and mass, energy. Okay, so, and now 2D. So remember 1D meant, for us, it meant a motion along a line in some direction. In 2D, this is motion in a plane. Okay, so we're going from an object having the ability to go this way or that way. It only has two choices, to now having infinitely many directions. So say like a bug on the blackboard, if it doesn't leave the, I guess that's a whiteboard. If it doesn't leave the whiteboard, it's moving in two-dimensional motion as it walks around. And from any point, it can move in infinitely many directions, okay? So let's think back just to connect 2D motion to the stuff we've been doing. In 1D motion, we had variables, or let's say mathematical quantities that had first a magnitude, and second a direction. I didn't talk about it this way very much. So what were the mathematical objects that we had that had a magnitude and a direction? Just numbers. Just numbers that had positive and negative worked in this capacity. The absolute value of the number you can think of as the magnitude. And then what about the direction? Well, the sign gives you the direction because there's only two directions. You can either go in the positive direction or the negative direction. In 2D, so let me add on to this. So the sign gives the direction because there are only two directions. And let me give an example of this. Sorry about making your notes messy, but let me give an example of this. You know, like, for example, something that's moving -6 meters per second. Means a magnitude, and if we're talking about velocities, that magnitude is called the speed, of 6 meters per second. In the negative direction. Okay. In 2D, we're also going to be working with these mathematical quantities. So we also have mathematical quantities with a magnitude and a direction. But notice that defining a direction in 2D gets a lot more complicated now. We can't, so let's say, but we can't use the sign for directions because now we have infinitely many directions. So like in 1D, if an object's here, it can either go, depending on what direction the line of motion is, it can only go this way or that way. Two choices. In 2D, if an object is here, it can go in infinitely many directions. These new 2D mathematical quantities are called vectors. And so before we get into doing calculations involving position, velocity, and acceleration, I just have to tell you about vectors and how to do math with vectors and how to interpret it. This is also what we're doing in lab this week. All of the class today and then all of the lab this week, we're just going to be trying to understand the idea of vectors. Okay, so vectors. In 2D, position, displacement, velocity, and acceleration will all be vectors. Vectors have two properties. The first one is magnitude. And the second one is direction. Bless you. And vectors can always be represented by an arrow. So we'll always represent vectors as arrows. So like, for example, this could represent a vector. As far as naming goes, the end without a point is going to be called the tail. And the end with a point is going to be called the head. The length of the vector is the magnitude. And I think the direction is pretty self-explanatory. It's just the direction that that arrow is pointing. Okay. To do math with vectors, we'll separate them into components. And these components are a piece parallel to the x-axis and a piece parallel to the y-axis. Okay, so for example, if we have a vector like this, and our coordinate system is this, the x component is how far you have to go along either the plus or minus x-axis. Okay, so this is the x-axis, this is the y-axis. This is the x component. And this is the y component. So notice where those come from. Just the x component is, you can think of those as projections onto the two axes. Okay, the blue is the black vector projected down onto the x-axis, and the green is the black vector projected onto the y-axis, how far you have to go. And these have positive and negative signs. So if this was over in another quadrant, the x component, like say it was in quadrant 2 over here, that blue part would be on the negative x-axis, and you'd have a negative component. The single most important thing to remember about vector components, so let's call this the most important fact about vector components. And that is, if you put the tail of the vector at the origin of your coordinate system, then the components of the vector are just the coordinates of the head of the vector. Okay, so for example, if your coordinate system is this, and the vector you want the components for is this, so let's say this is 1, 2, 3, and this is 1, 2, 3, 4, 5. So this is -5. This is +3. Then the components of that vector are -5 for x and +3 for y. Okay, so if you're comfortable getting coordinates of points, then it's the exact same procedure to get components of vectors. Okay. There are multiple ways to write components. Multiple notations for components. I'm going to give you two common ones, and then I'll tell you the one that I'm going to use. One that you see a lot, it would be to represent this as -5i plus +3j. And that this I says that's the x component. The y says that's the j, says that's the y component. I don't know where that came from actually, but it's a very entrenched way to write this. And so I'm giving this to you because if you go on to other physics classes or you have to take standardized tests or whatever, you're going to want to know that this means the same thing as this different notation we're going to use. But we'll use the notation where it's a vertical column matrix, just a column of numbers. The first one is the x component, and then the bottom one is the y component. And for now, there's not really any meaning to that. It's just a convenient way to write it. All you have to remember is that the top one is the x component, and the bottom one is the y component. You can think of it as kind of like the way you write coordinates, but it's a square bracket instead of a round, instead of parentheses, and it's flipped vertical. Okay. So this is the one we're going to use. One thing I want you to notice about this, so notice. By thinking of components as the coordinates of the head, you can always immediately tell the signs of the vector components. Okay, so let me draw a few vectors here. This is sort of like a example problem. What is the sign of each component? And so the first one is this vector. The second one is this vector. The third one is this vector. And the fourth one is this vector. So to visualize the signs of these, you can draw it or just imagine it. Put the coordinate system at the tail of the vector. And then you're just trying to figure out what quadrant the head of the vector is in. So for the vector for A, is the x coordinate of the head positive or negative? I know somebody knows this. I know it. Yeah, thank you. So negative x component, and is the y coordinate of the head positive or negative? Positive. Okay. And now we'll go to B. Is the x component positive or negative? Negative. What about y? Negative, yep. And then for C, the x component, positive. Y component, positive, yep. And the last one, x, positive, yep. Y? Negative, perfect. Anybody have any questions about that? So you definitely want to be able to look at a vector and just, intuitively just eyeball what the component signs are. And this is how you do it, by thinking about it as coordinates of a point, okay? So here's something that'll also be really useful. What about vectors? So all of these, notice, were in between coordinate axes. What about vectors that lie on coordinate axes? So like, for example, what if you had a vector like this, and you knew that its magnitude was 5? What would be the coordinates of that vector? If you think about that as coordinates, put the tail at the origin. You want the coordinates of that point there. So what would the coordinates of that point be? We know that the length is 5, so it's going 5 in the negative y direction. Yep, 0 for x, that's right. So the coordinates here would be 0, negative 5. And so the components are 0 on top, negative 5 on the bottom. What about a vector like this with a magnitude of 3? That's supposed to be horizontal. So here's the coordinate system. Put the tail at the origin. What are the coordinates of the head of the vector? Yep. Yep, exactly. So there's the coordinates. And so what that means is the vector components are 3, 0. Pretty often, you're going to, okay, so if you're given a vector as a length and an angle from some reference line, you're going to see this all the time. So like, for example, the reference line in this case is just the vertical. And say that you're given a vector and told that it has a length of 10 and it makes an angle of 20 degrees with this vertical. Then in order to come up with the components for this, first find the counterclockwise angle from the positive x-axis to the vector, and we're going to call that angle theta. And then the components of the vector are going to be L times the cosine of theta, L times the sine of theta. And I'm not even going to go into the trigonometry, the meaning of sine and cosine, but these are just the sine and cosine are just things you can plug into your calculator. I think most people in this class have seen those before, but not all. One thing is, in this class, we're always going to do our angles in degrees. So make sure your calculator isn't in radians, or things will look really confusing. So make sure your calculator is set in degrees. And if you're not sure how to change that, well, it's usually under a button called mode on most calculators, but I'd be happy to show you how to fix that if you can't see it. And remember, the meanings of these are, this is the x component, and this is the y component. Okay, let's do an example. And I'm just going to use the example that I gave above. So say that we have, we know that our vector has a length of 10 and makes an angle of 20 degrees with this vertical line. Okay. Whenever we're trying to figure out vector components, we're going to put the tail of the vector at the origin. Okay. And now, if you look back at the steps, so we know this angle is 20 degrees from the vertical to the vector, but we want what we want to know is if you start at the positive x-axis, how far do you have to go counterclockwise until you run into the vector? Okay. And so what we want to know is this angle. And one way you can think of it is clockwise always means negative, counterclockwise always means positive. So you can think of it as you start at the x-axis, you go positive 90 degrees, and then you backtrack negative 20 degrees, which means that this angle is 70 degrees. 90 minus 20. So this is the theta we want. And theta is equal to plus 90 degrees minus 20 degrees, or 70. So now to get the vector components, we're going to go 10 times the cosine of 70 degrees for x, and then 10 times the sine of 70 degrees for y. And that is 3.42, 9.40. Anybody have any questions about that yet?
Yeah, I didn't understand it at all.
Okay. Okay. Well, so if you have a calculator in front of you, it doesn't look like you do, but there's a sine and a cosine button.
Yes.
Okay. So we want to find the angle where if you start as the positive x-axis, so the positive x-axis is going this way, right? And now we want to know how far we have to rotate it counterclockwise to match it up with the vector.
Okay.
And so, you can think about that a few different ways, but you know that this angle plus 20, you have to add up to 90 because this and this are 90 degrees apart.
Yes.
So that has to be 70.
Okay.
And now you're just going to plug in, so the magnitude is 10.
Yeah.
You're going to plug 70 into the cosine and multiply that answer by 10.
Gotcha.
And then for this 70, you're going to do the sine of 70, multiply it by 10, and your calculator tells you this. And that's all you have to really think about it.
Okay.
But one thing to keep in mind is when you do these components, like I said before, you can always tell whether the signs of the components came out right. You can't automatically tell whether the values came out right, but you know that the coordinates of this point need to be positive because it's the first quadrant. So just take a second and just do that as a sanity check. A lot of times what that'll catch is that your calculator is in radians when it should be in degrees. Okay, so if the signs of those components don't make any sense, either you punched it in wrong or your calculator is in radians. By the way, you could also find the clockwise angle from the positive x-axis to the vector. But then you just have to call the angle negative. So in this case, this would be a weird one to do it on because it's a lot easier to figure out this angle going this short distance than to figure out how far you have to go clockwise all the way around. But there is a clockwise angle you could go around, and it's 290 degrees, you know. And so if you called theta, instead of calling it positive 70, you called it negative 290, you could plug that into this same formula and get the exact same answers. Okay. So sine and cosine are just magic, that's all. And your calculator does it, you know, for you, luckily. All right, let's, I'm going to write up a couple of example problems and give you a little time to try to think through it. Hold on. So find the components of, so the first one is a vector that has a length of 5 and makes an angle of 30 degrees with the horizontal. And second, a vector that has a length of 10 and makes an angle of 20 degrees with this vertical. Okay. So if you don't have a calculator here, just try to figure out what the angle theta needs to be for you to do this calculation. Punching it into the calculator is sort of the easy part. Okay, so for the first one, our coordinate system is like this. The vector is this. This angle is 30 degrees. So to go from the positive x-axis to the vector, what's the theta we need? 30, positive 30, because it's counterclockwise. And so the components are 5 times the cosine of 30, 5 times the sine of 30. And if you plug that into your calculator, you get 4.33 and 2.50. Anybody have any questions about that? Yeah.
Why is it not 60? Like how you did up there, you did like plus 90 minus 20 is 70.
Right. Yes, because yikes. Okay, it's so always what you're trying to do is just think of starting with with an arrow in the positive x direction, and then rotate it counterclockwise until it matches this. In that case, this is the angle that you go through. It's just at 30. So this is 60, but that just doesn't come into it. So just, put the arrow in the direction of the positive x, and then see how far you have to rotate it until it runs into the vector.
Why was the other one different? Is it because we have to go from the y and go down?
That's right, because, let's see. That's right, because, so it would have been 20 if what you had to do was start at the positive y and rotate clockwise to hit the vector, but that's not what we do. We start here and go this way. So we need to know this angle, and that's not this 20. So we have to figure out based on that 20 what it is. Okay, so now part B. So the coordinate system is this. And the vector is this. And we know this angle is 20 degrees. The magnitude is 10. All right, so we have to figure out how far we have to go from the x-axis counterclockwise to run into that vector. So start here, and you go 90 to get here. And then we have to keep going.
Why don't you go down?
We can go down and call it negative. That's fine. Let's do it both ways. So here, but counterclockwise is positive. So so we'll go 90 and we're here. 180 and we're here. Okay, and then so we're at 180 pointing this way. And now to match up with the vector, we have to go this much farther, which is 90 minus 20. So it's 180 plus another 70, so 250 degrees. So if we start at the x-axis and go around counterclockwise, it's 250 degrees. If we went clockwise instead, start at the positive x-axis, and we have to go clockwise 90 degrees to get there, and then clockwise another 20 to get there. So it would be negative 110 degrees. And if you plug those into cosine and sine, they give you the same thing. So the other answer could be theta is equal to negative 110. And so now put those into cosine and sine, and you get 10 times the cosine of 250, 10 times the sine of 250, is equal to negative 3.42, negative 9.40. Any questions about that one? And then the last one, so our coordinate system is this. Our vector is this. And it has a magnitude of 3. Okay, so there's two ways you can think about this one. And the quicker, easier way is just to think, okay, that's in the positive y direction. So these components are going to be 0, 3. Okay, but you could also think of it 0 for x, positive 3 for y. Okay, so you could also think of it in terms of the angle. What's the angle counterclockwise that you have to go take the x-axis to make it match up with that?
Mm-hmm.
90, yep, positive 90. So it would be 3 times cosine of 90, 3 times sine of 90, and it would give you 0, 3 either way. Okay. I know this is getting long, but there's one more thing I have to tell you about, and then we'll talk about how to do calculations with vectors. The last thing is, in math, you probably never really used any coordinate systems that were not oriented like this. So here's sort of like the last new thing about vector components. And that's rotated coordinate systems. So coordinate systems don't have to be in the directions that you're used to. You can, as long as, let me say it as, so dot, dot, dot. They can also be rotated versions of this. Okay, so what if, I'm just going to do this as an example and just show you sort of how to think about this. So like, what if your vector that you're interested in, you knew it made a 40-degree angle with this horizontal, and it had a magnitude of 10. And we're going to do it for 3 different coordinate systems. So what are the components of this vector? First, in the usual coordinate system, second, let's rotate this coordinate system so that the positive y-axis is pointing this way. And that means that the positive x-axis is pointing down. And third, let's do it for a coordinate system where the x-axis is pointing this way. I don't know why I changed colors. And the y-axis is pointing this way. And this angle is 40 degrees from the horizontal. Why would we ever want to do that? That's not clear yet, but we'll see that it's useful eventually. Okay, so the first one, this is the stuff we've been doing. So I'm going to draw the coordinate system, put the tail of the vector at the origin, and we know that this angle is 40 degrees. If we go counterclockwise from the x-axis to the vector, that's 90, 180, 220. And so this is going to be, the components are going to be 10 times the cosine of 220, 10 times the sine of 220. And that comes out to be negative 7.66, negative 6.43. Now we're going to go to the funky ones. The first one isn't so crazy. it still lines up kind of the way we're used to. We're just calling the x-axis down and the y-axis to the right. And the vector does not rotate when the coordinate system rotates. So this vector still just points just like this. And it has a magnitude of 10. And it makes a 40-degree angle with the horizontal. But now to do that angle theta is going to go from the x-axis of this coordinate system to the vector, okay? So you can either start pointing down and go all the way around, or you can start pointing down and go clockwise and call it negative. What would be the angle if you went negative to get to the vector? Negative 50, exactly. If you went all the way around, it would be 90, 180, 270, 310. So negative 50 or positive 310. So we went this way. So theta is equal to negative 50. And so the components in this coordinate system are 10 times the cosine of negative 50, 10 times the sine of negative 50, and that is positive 6.43, negative 7.66. Any questions about that one? Okay, the last one. So now this is the one where the coordinate system is at this funny angle, right? So the coordinate system looks something like, yikes, this. And this makes an angle of 40 degrees with the horizontal. And now our vector makes an angle of 40 degrees with the horizontal going the other way. And so if I continue this horizontal, the vector goes straight like this. And has a magnitude of 10. This angle is 40 degrees. And so now, what are the components of that vector in this rotated coordinate system? It's just pointed straight along the negative x-axis. And so we can just write this right away as negative 10 in the x direction, 0 in the y direction. Yes? What? Yeah, right. It's not very clear yet, but it will be clear. I mean, it'll be useful once we get to forces of objects rolling and sliding on inclines. That's when we're going to use it. For now, I'm just kind of introducing like some ideas of vectors, some things we can use. Mostly we're going to use normal coordinate systems, but there'll be a few times where we use these rotated coordinate systems. Any other questions right now? Okay. Let's stop there. Everyone's tired of this. So, but I have some problems I'll give you that'll be due on whatever day it is, +2. Thursday. Okay.